Okay, let's get started. So let me begin by expressing how delighted I am to be here. Thank you, the organizers, to invite me. It's been fascinating to hear about this very vast range of turbulence phenomena. Certainly, I have known only very little about some of them, and so I have been learning, and it's been fantastic to interact with people. So, happy birthday, Srini. I hope that you will continue to contribute for many decades to come. I look forward to our interactions. You have always been very kind and inspiring, setting standards for others to learn from. So I'm going to be sharing some work that we have done over the years, and I thought that this is a good time to sort of revisit some work that we've done over the years. So explain the title a little bit as we progress. And this is work done in collaboration with a number of people. Britton Olsen's work will be highlighted. One former student, Johan Larsen, Ivan Bermejo Moreno, postdocs, former student, and my esteemed colleague, Parviz Moin. I bring his regards to you. Okay. Point over here. All right, so what I would like to do is we'll start with a glimpse of phenomena where compressibility effects are important. And then, I'll purposely make this presentation a little bit more pedagogical than a research presentation, and I'm doing this with the idea that perhaps not everybody in the audience is an expert in the topic, and so that's the orientation. And so about half the talk would be in sort of summarizing results that are known, and I would call that fundamental picture, and then discuss some highlights from some more recent studies on homogeneous turbulence, shock turbulence interaction, and a bit of this topic, which I know is of interest to many here. So some years ago, 1994 was the year when I was invited to write an article for the Annual Review of Fluid Mechanics with this title. And it's been a few years since that time, and much more has been done on the problem in the last couple of decades. And so that's what I would try to revisit, the progress that has been made. Okay, well, this doesn't work. So problems in aerospace applications, rocket propulsion, high-speed vehicles involve flows that, if you think about a hypersonic vehicle or supersonic mixing in scramjets, involve injection of a fuel jet which has to mix with a supersonic cross-flow, and you can imagine the interaction. This is an example from work that we did with Soshi Kawai. It's a large eddy simulation study. There are other problems involving shock boundary layer interactions that you can imagine occurring around the surface of a vehicle and so on. And so the reason I'm sharing animations like this is to sort of indicate to you that overall the phenomena are complex. There are many kinds of things that are happening. And in thinking about problems of interest from engineering perspective, one needs to think about the overall problem as well. Specific interactions of how turbulence interacts with a shock, or how shear layers behave under compressible conditions and so on, are idealized problems and so on, but in engineering, it's the overall problem which matters quite a lot. Here are a few more examples. This is an example up on top of a pressure mismatched jet coming out of a nozzle. And the pressure mismatch produces these shocks. Shock causes boundary layer separation. That separation moves around because the shear layer doesn't reattach, and so there is a rather large blockage produced by this low velocity region. And so the expansion that the flow sees is highly dependent on how much the flow spreads. And this whole system is a coupled system which oscillates, and hopefully you can appreciate some of the dynamics that are taking place. This is simulations, and perhaps it's good to sort of reflect on the fact that now it's possible to do simulations that, when viewed, sort of remind one of things that one would see in experiments and so on. So it's computational capability has come to a point where one can do problems of this kind and make some sense out of what's going on. And we have studied that and so on. But rather than talk about sort of an applied problem with sort of overall engineering application, I'll try to sort of talk about things that are more fundamental, that are pieces of the overall puzzle that one needs to deal with. Of course, there are applications in astrophysics, and there are lots of people here who know lots more about this than I do, so I'll not say a lot other than saying that there are interesting applications involving solar convection, supernova collapse, density fluctuations in interstellar medium, and this problem, which is a problem of implosion of a capsule of fuel. It's hydrogen deuterium capsule driven by plasma that is generated by focusing all these lasers and causing collapse of that capsule. The idea is that that collapse by a shock wave is going to compress the material inside to such high densities and pressures and temperatures that nuclear fusion will take place and produce energy and so on. So this is sort of the inertial confinement fusion problem, which involves extreme compressions of materials. And anytime you have a system of this kind, interfaces are never perfect. And this involves multi-material capsules and so on. And so anytime there's a misalignment between interface gradients and shocks, turbulence comes up. Baroclinic generation of vorticity is a very important phenomena that takes place, which doesn't require compressibility, but misalignment between pressure and density gradients. So let's capture a few fundamental ideas. And back from the late 1940s, early 50s, the idea has been to think about the fluctuations in a turbulent medium in terms of a decomposition, a three-mode decomposition, a vertical mode, acoustic mode, and entropy mode. Well, vertical mode is a solenoidal velocity field. It has all the vorticity, but in this decomposition, it has no pressure fluctuation. So it's a little bit incomplete in terms of suitability for describing turbulence. Acoustic mode carries all of the pressure. It is irrotational, and of course, there's density and temperature fluctuations that are isentropic. And entropy mode has all the entropy fluctuations and no velocity and pressure. Of course, this modal decomposition is perfect for disturbances about a uniform state, but only when the amplitude of the disturbances are small is this modal decomposition very useful. And as amplitude grows, and in presence of mean gradients, mean temperature gradients, mean density gradients, mean pressure gradients, all these modes couple in a strong way. And so the problems that I showed you animations of before fall beyond where this kind of decomposition is useful, but this decomposition is certainly useful in certain regions of the flow, and that's how it's used. Well, let's think about compressible turbulence by contrasting it with incompressible and variable density turbulence. Well, incompressible turbulence we can think of as strongly nonlinearly interacting vertical modes. The notion of vertical modes now extended so that pressure effects are included. And of course, if you think about a wave space velocity field describing the turbulence, then the associated pressure is very naturally contained in that description. And that gives rise to a non-local coupling, which is a difficulty of turbulence beyond the nonlinearity. Nonlinearity and non-locality being the two fundamental turbulence problems. Variable density turbulence then is a low Mach number flow turbulence that has significant density variations, but no acoustic perturbations, no acoustic coupling. And it's relevant for reacting flows, for example, or mixing of different materials that have different densities to begin with. So compressible turbulence now is turbulent flow where fluid parcels, as they move around, change their density in response to pressure variations. Of course, fluid parcels move around in response to pressure variations in an incompressible flow, but in incompressible flow, their density doesn't change. When the pressure changes are significant enough to cause density variations, that's when it becomes compressible. All right, so of course, in this context, there's a very interesting theory that was developed by Ristorcelli in 1997, which makes use of the idea that at small turbulence Mach number, if we define a turbulence Mach number as a Mach number based on the fluctuating velocity divided by the speed of sound, when that fluctuating Mach number is small, one can think of the turbulent fluctuations as essentially incompressible, and associated with that incompressible fluctuation, there is pressure variation. That pressure variation accounts for a variation of density. Okay, what did I press here? We are still okay. One can think of that induced motion, compression and expansion of fluid in response to pressure, but pressure at leading order is determined by incompressible considerations. And so that's why it's thought of as enslaved dilatational motions, enslaved to the vortical motions that are leading order behavior at small Mach numbers. Of course, one can talk more about other sort of systems of linearized descriptions and so on, but they have their limitations in that linear theories describe linear phenomena. Turbulence, one could say maybe there are parts of behavior of turbulence dynamics that can be described as linear, but certainly the central problem of turbulence is not linear. Okay, so moving on. It's important to think about the energy transfer pathways that are active. And of course, it's traditional to use this density mass weighted or density weighted Fabra decomposition to describe the velocity, mean velocity, and perturbations from mean velocity. So one can think of the mean motion in the flow that has a kinetic energy or the mechanical energy, and that mean state also has internal energy, and these two can interchange with each other in terms of pressure work. It provides rate of transfer between them, and that's a reversible process. This is a process that is active in a non-turbulent flow as well. In an inviscid region of the flow, if Mach numbers are significant, there is a conversion of mean mechanical energy into mean internal energy and backwards as well. Of course, turbulence sort of complicates this picture. There is turbulent kinetic energy, which is generated by the processes of turbulence production. And then through cascade processes, this kinetic energy is dissipated. And so, of course, there is the TKE dissipation, which is solenoidal. But in a compressible medium, there is additional dissipation due to dilatational fluctuations. And when there are shocks arising as well, then there's shock-led dissipation as well. So dissipative processes are modified by compressibility to some extent. Going back to Fabra's original 1960 work, there is also this additional reversible transfer pathway, which Fabra called enthalpic production of TKE. This is a terminology called baropycnal work, which is now being used. What is it? If we think about density variations in a flow, and responding to pressure variations, fluid parcels that are lighter are going to accelerate more rapidly compared to fluid parcels that are denser for a given pressure imposition. And so therefore, there's differential acceleration that is coming about, and that differential acceleration provides a work transfer between internal energy and turbulent kinetic energy. And that is what is baropycnal work. And of course, there is pressure dilatation work, which involves compression, actual compression and expansion of fluid elements. And that is also reversible, as shown in these arrows. And so with this, let's continue. So yeah, question. Yes, it does, and we'll see examples of that as we progress. we can think of compressibility as modifying the energy transfer from the mean into turbulence, sort of the large-scale energy-containing processes. It may modify the cascade processes, and it may modify the dissipative processes. So it may affect different scales of motion differently, and one can characterize that specifically, and we will talk about that. All right, thanks. And if there are other questions, please do interject. If this becomes more of a dialogue, I'll enjoy it much more, and I'm sure you will enjoy it as well more. So we can think about different non-dimensional parameters to characterize compressibility effects. In terms of overall mean, we can think about velocity scale in terms of mean velocity variations. So in case of a shear layer, there are two free streams. So velocity difference normalized by some speed of sound defines a relative Mach number or a convective Mach number. We'll say much more about this as we go along. Of course, there's turbulence Mach number, velocity fluctuation scale divided by the speed of sound. That's a turbulence Mach number. And the idea of a gradient or deformation Mach number is something that got introduced in the late 80s into the literature, and this is not as widely used, and I'm talking about it here more so that maybe in broader community it could be used. The idea is to define a Mach number which is based on the rate of strain or shear or some deformation rate and the turbulence length scale and the speed of sound. So why it might be important to think about a deformation Mach number or a gradient Mach number. One can think of such a Mach number as a ratio of time scales. L over C is an acoustic time scale, time for acoustic travel across a turbulent eddy of scale L. All right? And the deformation time scale is here at the bottom. So it's the ratio of acoustic communication time across the eddy divided by the deformation time. And so if the deformation is very rapid, so rapid that there isn't enough time for sound to communicate across the scale, eddy scale L, then this is going to be a very different kind of beast than a regular hydrodynamic turbulence. And so this gradient Mach number or this deformation Mach number is a useful way to think about whether the eddies behave as if they are quasi-incompressible or they become, their character changes dramatically and it becomes something very different, which is the situation when this gradient Mach number becomes appreciable. And so this is something that should be used more, but so far it's used only in some literature, and hopefully it will spread. Back from 1977 at least, following Peter Bradshaw, it's useful to think about a friction Mach number, a Mach number based on friction velocity. U tau is the velocity scale associated with friction divided by speed of sound. And one way one can think of this as immediately being useful is providing a contrast between a mixing layer and a boundary layer, turbulent boundary layer behavior. If we make simple estimates for the friction velocity, in a mixing layer, friction velocity normalized by the overall velocity difference, you would get numbers like this. I mean, we can, I'm quoting only one digit. Of course, one can characterize this better if I specify what kind of flow it is. I say mixing layer. So shear layer or mixing layer has a momentum flux going from high speed stream to the low speed stream. So that Reynolds shear stress could be used, or that's the shear stress. One could derive, assuming some density, one could derive a U tau based on that. It's not traditionally done, but it should be done. For a boundary layer, of course, this is very common. And so then if we say that we want friction Mach number to be comparable between a compressible boundary layer and a compressible mixing layer, then given this difference, you can see that in a turbulent boundary layer, you will need at least a factor of 5 more free stream Mach number in order to have the same m tau. And that is something that is very prevalent in the data. In compressible mixing layers, as soon as the convective Mach number or relative Mach number exceeds something like 0.4, 0.5, there are dramatic compressibility effects. But in turbulent boundary layers, even at Mach 10, free stream Mach number of 10, intrinsic compressibility effects seem to be completely absent. So based on this, we can argue that up to 5, there shouldn't be anything. Why is it that even at 10, there isn't anything? And that requires some thought. And it's very relatively simple. Of course, in the near wall region, there is very intense aerodynamic heating, and the consequence of that is the very low density and a region of high viscosity near the wall. And so this has an effect, which we will talk a little bit about further, which sort of extends this factor up further, and up until 10, there has been simulation exploration, and no intrinsic compressibility effects are observed. Of course, I'm not saying that the turbulence is not changed by this dramatic variation in density and viscosity, but the variations up to Mach 10 in turbulent boundary layers that have been observed can be entirely explained on that basis. That is what Morkovin said in 1962 and has been verified in all subsequent work. It's telling us that because of the wall, velocity fluctuations are required to vanish. A normal velocity cannot cross the wall, and that has a long-range effect on the nature of the turbulent motions in the boundary layer, which constraint is not present in shear flows, in free shear flows. Okay. So, continuing on this thought, let's talk a little bit further about the difference between shear layers and turbulent boundary layers. This classic paper by Brown and Roshko, 1974 in JFM, which is one of the most cited papers in JFM, showed that the suppression of spreading rate when the two streams became supersonic, when the relative Mach number became higher, was not due to a density variation. It was a compressibility effect, and they attributed the compressibility effect to pressure reduction. And these pictures I've taken from the study by Papamushko and Roshko, 1986 in JFM, where they introduced this idea that really one should be thinking about this problem in a relative frame of reference, in a frame of reference intrinsic to the large eddies. The large eddies are moving at some velocity. The Mach number seen by the large eddy depends on the relative velocity in this frame of reference, and that's kind of a cartoon in this frame of reference, and then the velocity difference divided by the speed of sound. You could divide it by this speed of sound or that speed of sound, and it's possible to sort of arrive at such a formula by sort of following what's happening to a fluid parcel starting over here and stagnating, following an isentropic process, and likewise on the other side, and that's the argument that Papamushko and Roshko made. The dramatic result that they showed is that the normalized spreading rate, a spreading rate of a compressible shear layer normalized by a shear layer which has the same velocity ratio, little r is the velocity ratio, and little s is the density ratio. That normalized spreading rate has a collapse of this kind, that above 0.4 or so, the spreading rate is suppressed, and then at convective Mach numbers beyond 0.8 or so, there is roughly a factor of 5 or so reduction in the spreading rate, a dramatic reduction in spreading rate with two notable features. One is onset around 0.4, 0.5, and then a saturation at higher convective Mach numbers. And these are things that one would like to explain by physical arguments. What is happening to turbulence which brings this about? All right, so this is one example where compressibility effects on the overall flow are rather dramatic and well defined. So a number of ideas have been put forward in the literature. Early on, Otto Zeeman and Sutanu Sarkar and collaborators proposed the idea that really it was additional dissipation due to dilatational motions and shocklets that was the source of reduction of this growth rate. Well, that's a nice idea, but later work has shown that if you actually calculate, if you evaluate what these are, how much they are, they turn out to be too small, way, way too small to explain this behavior. Another popular idea in the late 80s was that shear layers radiate sound, and that sound would carry energy flux with it, and maybe it is that which is causing growth rate suppression. But again, one can do an energy budget, find out how much power is being transmitted by acoustic radiation, and that is very small, extremely small, even much smaller than this dilatational and shocklet mechanism. Of course, many groups have, yes? Yes. No. The most dominant effect in hypersonic boundary layers is the fact that aerodynamic heating is producing strong density variation. It's very low density region near the wall, and high, or viscosity is also very high because of high temperature, and both are causing a change. So it's a variable property effect and not a compressibility effect. So suppression of linear instability has been linked to or suppression, meaning growth rate is reduced with Mach number. It's not suppressed entirely. That is similar to the observed shear layer spreading rate reduction. But this is sort of saying that, okay, one problem is analogous to another problem. It doesn't really explain why it happens. Why is it that the linear instability has this behavior, for example? So that needs further probing. Later, a few years later, Riemann and Pantano and Sarkar, both in JFM, showed that really is the structural change in turbulence, a structural change in multiple ways, multiple aspects of the turbulence structure changes. Turbulence and isotropy changes as the convective Mach number increases, but also the turbulence eddy structures become more anisotropic in their length scale as well. And we will talk about this further. And yesterday we heard about this explanation in terms of pressure suppression causing pressure strain rate suppression, causing production suppression, and so on. It's all linked to the change in the turbulence, which we can now think about in terms of the explanation. In the early 90s, there was another hypothesis called sonic eddy hypothesis from Bob Breidenthal from University of Washington. Bob came up with this very simple idea that turbulent eddies that are actively entraining cannot have a velocity difference across them that is more than the speed of sound. And the idea is that if the velocity difference across an eddy is more than the speed of sound, then they will not be able to communicate induction, vortex induction or Biot-Savart induction, which we use to think about the kinematics relationship between vorticity and velocity, is fine for incompressible flow or low speed flow. As you go compressible and high speed, one has to think about acoustic processes as well. And so this idea was put forward by Breidenthal. And so in subsequent time, some of these explanations have kind of merged into a picture, and that's what I would like to share. And so this is based on work that Jonathan Friend did for his thesis with us, published in 2 papers in JFM. And I'm not showing all the details. Jonathan showed that indeed the suppression, the spreading rate suppression as a function of convective Mach number was observed in the simulations. I'm not showing that detail. I'm showing you 3 images from 3 flows. He had computed many more: a low convective Mach number, a convective Mach number of 1, and a higher convective Mach number. And hopefully, just from these images, which are passive scalar cuts, you get an impression of the change in the turbulent structure that is taking place. Low convective Mach number, these things look much more like Kelvin-Helmholtz billowing kind of motions and so on. And notice how they change as Mach number increases. These things become more wispy. Their scale, transverse scale across the flow shrinks compared to the scale that one had. These plots that you can't see, I am purposely made it light. These plots indicate that the dilatational dissipation and the pressure dilatation quantitatively is orders of magnitude too small to explain the growth rate reduction that is observed. How do we think about this reduction that is taking place? Well, we quantify the transverse length scale, a correlation between a fluctuating velocity in the normal direction to the shear layer with a separation in the direction across. And so that length scale, as a function of convective Mach number normalized by the thickness of the layer, decreases substantially as the convective Mach number increases. So this is not unlike similar phenomena that happen in stratified flow, where the Richardson number, once it is exceeded, there is this layering tendency that happens in stratified flow. Of course, there is no mathematical analogy between this problem and the stratified flow problem. I'm just drawing the analogy in terms of turbulent structure change. What is happening here is that pressure is controlling the action. And so if we think about how intense pressure fluctuations are as a function of convective Mach number, you can make an estimate for pressure fluctuation by thinking about, if we say that there was active overturning on full scale, the scale delta, then based on the velocity difference between the two streams, you could say that there is a dynamic head associated with that velocity difference, and you could say that pressure should sort of scale with that if the density was more or less constant across the flow. And that would be this estimate, this dashed line that is going up, and that's a way overestimate. Pressure does not scale anything like the dynamic head. It's much less, and what it is that there is this transverse length scale that I showed on top, which is being suppressed. If we take the velocity difference across this transverse length scale and compute the dynamic head associated with that, and say that pressure scales with that dynamic head, that is what we find. And so then the question is, what is this length scale? And we find that, in fact, if we find a gradient Mach number based on this length scale, we get a gradient Mach number which is saturating. And so it's looking like there is this acoustic communication, a kind of blockage that is coming about. Eddies that are able to form and overturn are able to do that only by having effect of that eddy being felt on the scale of the eddy, and that is constraining the length scale. Yes? Mm-hmm. There's no change in that. It's only if the densities are also different. If there's a rho 1 and a rho 2, then the flip experiment doesn't have the same, the spreading rate is not exactly the same, but one can figure out how much change happens by thinking about, if you think about the evolution in a convected frame of reference with the large scales, there the flip doesn't have an effect. So because of asymmetry in the spreading in the spatial mixing layer, there is actually a density ratio effect, which is well known and studied by. There is a density ratio in here, and in these pictures, I should have explained the flow configuration a little bit better. This is an annular configuration. The middle of the flow has a higher speed, and the outside stream has a lower speed or zero speed in some situations. It's sort of like the early portion of a jet, except that we are using periodic boundary conditions in this direction, and so we can use Fourier methods in this direction. And the jet is not spreading as a function of space, it's spreading in time, starting with a narrower jet. It's like a temporal problem that is studied. Okay, if there are other questions, Srini is being tremendously helpful here. I'm sure there are others who have some questions too. Yeah. Go ahead.
Hello. Yeah, thank you for the talk. So I'm curious about the reactive flows, compressibility effect in reactive flows. So generally, when you have, especially in the case when you have, when the reaction time scales becomes very small, like smaller than the dynamical time scale or some mixing time
Right.
scale. In that case, the compressibility on because of these small explosions could in potentially give
Well, so let me say a little bit about reacting flows. Well, reacting flows have additional non-dimensional parameters. There is the Darmkoller number that one needs to characterize. And of course, real chemistry may involve many species that have to be tracked and so on. Multi-component diffusion and so on may be important. Often, reacting flows are in a regime where reactions themselves are not affected by compressibility, and it's the flow which brings the fuel and oxidizer together, and they mix and burn or react. But in scramjet mixing, that mechanical mixing is what is being changed by compressibility. Okay, maybe we can talk more afterwards.
Any more questions?
Okay, have I used up all of my time? If I have, I'm awfully sorry, because looks like we didn't even finish the quote-unquote fundamental picture. So I guess I should have planned to be more compressible than I was. But hope that you got some ideas across. So if you can indulge with me, I will switch to the very end here.
So actually, you can take 5 more minutes.
Okay, thank you. So we'll complete the fundamental picture and not worry about more recent results. So this is the contrast to compressible shear layers, and the Van Dries transformation is collapsing velocity profiles from incompressible to Mach 12 boundary layer flows onto essentially the same curve. And so this is, Srini, the variable density effect that in an adiabatic wall boundary layer is explaining all the velocity profiles. And similar explanation for the turbulent fluctuations is also available. So on the left is the variation with Mach number, and that variation is essentially removed. This is taken from Dewan and Martin's paper in JFM. These things are scaling with local density, essentially saying that there is a constant stress layer, and so the velocity fluctuations scale like 1 over the square root of density. Once you take that into account, this collapse is achieved. And so up to 12, Mach 12. This is all adiabatic walls with heat transfer on the wall or with reactions or heat release in the bulk of the flow. This needs to be extended and has been extended recently in work by Pecknick and Patel and by Trittel and Larson at University of Maryland. Very exciting work that has been published in the last couple of years. So let's end by going to the summary here. I guess the only way we can get to the summary is by running forth. I didn't show you any shock turbulence interaction problems that we have done, I think, interesting work on. What is this? I can't see what is on the screen. What does it say? Summary, okay? So I think their physical understanding of compressibility effects has improved over the last couple of decades. DNS, LES numerical simulations have really come along and provided very useful insights. But Reynolds number, of course, remain limited, and there are many dimensionless parameters. I only described a few. There are other dimensionless parameters that are important that characterize initial conditions, boundary conditions, and so on, that have an influence, and so they have only been limited exploration of that. I would say that the theoretical framework is still quite insufficient, and one thing in which it lacks is there's no formal theory that is able to take into account this acoustic communication requirement for vortex dynamics, a systematic accounting of it. Of course, at the Helmholtz decomposition level, a velocity field can be decomposed into vorticity and or rotational and irrotational velocity, but they are not uncoupled. As the velocity field evolves, the velocity potential and vorticity are coupled to each other. And a good model of it that is simpler than solving the full equation is not available, and engineering models that incorporate this physics are coming along, but more progress is needed. And I think simulations have given us some interesting physical ideas about what is happening, but they are yet to be confirmed experimentally. I mean, these ideas that I mentioned of a length scale of turbulence overturning, length scale being limited by acoustic communication, is something that is yet to be experimentally verified. And likewise, other things that features on spectra for the dilatational component of the velocity fluctuation, a slide which I didn't get to show you. There has been quite a bit of work on that topic in the last 10 or so years, is yet to be verified experimentally. So with that, let's close. Thank you for your patience.
So since we are running behind time, maybe one last question.
This is from the mixing layer point of view. Are there any attempts to describe or explain the reduction in spread rate from the thermodynamic quantity statistics?
Well, so when thermodynamic fluctuations and velocity fluctuations are coupled to each other in a compressible medium. And so it's not that one could explain it only from one point of view. It has to be a holistic explanation, and maybe we can talk about that more.
Yeah, sure.
Yeah? Sure. Well, I mean, I would say that 1,000 cube simulations of compressible turbulence that have been done in the last few years have shown that energy spectra is consistent with Kolmogorov inertial range scaling, and the compressible part or the dilatational part can also be explained using scaling arguments that have been developed theoretically, but we can talk about that later.
I think other question can be addressed in the T session. So let's thank the speaker again.